I'd like to put together our definition of a system of objects, our definition of the center of mass of a system of objects, our knowledge of Newton's third law and N2L force pairs, and our knowledge of Newton's second law, put all that together to derive a new, more powerful version of Newton's second law that we can apply to the motion of a system as a whole. So here's how the derivation goes. I've got an example system here consisting of three objects, A, B, and C, and I'm showing the free body diagrams for each of those objects. So A here is experiencing an interaction with C and an interaction with B, is being pulled or pushed towards C and pushed away from B. And so since these interactions are with other objects inside the system, these are internal forces, and I'm drawing all the internal forces in blue here. So that is the force on A due to C. And then, of course, if we look over at C, we see the partner force, the force on C due to A, for that Newton's third law internal force pair. Likewise, here's an N3L force pair, internal forces between A and B. Now, A is also interacting with something outside of the system. This is an external force right here in red. So I'm going to call it force 1. So two internal forces and one external force. Likewise, if we look over at C here, it has two internal forces from interacting with B and A, and two external forces from interactions with things that are outside the system somewhere out here. B just has those two internal interactions with A and C. It's not interacting with anything outside the system. All right, so I would like to look at what happens if we add up all 9 of these forces. If we look at the net force on the whole system. So by the net force on the whole system, I mean the sum of all the forces on A plus the sum of all the forces on B plus the sum of all the forces on C. Let's look at that list of terms. So here are the forces on A, the forces on B, and the forces on C. And you can already tell that when we add all these up, those Newton's third law force pairs, those equal and opposite forces, according to Newton's third law, will cancel each other out. So the force on A due to C and the force on C due to A, those will cancel. FAC and FCA, those terms cancel out right there. Likewise, FAB and FBA, that pair will cancel out. And FBC and FCB, that's an internal force pair that'll cancel out. So all these force pairs, the internal force pairs, will cancel out, leaving just these 3 external forces. In other words, if we add up all the forces on our system, what we get is just the sum of the external forces. And this is a key concept. The net force on any system is equal to the sum of the external forces because the internal pairs cancel out. Now, I did this derivation for this example system with 3 objects, but it applies and generalizes to a system of any number of objects. Okay, so let's take that idea and now look at the center of mass of the system and the acceleration of the center of mass. I've indicated that imaginary point right here, and we know that as A, B, and C move around, as the objects move, the center of mass will move as well. We want to track its motion. So to find the acceleration of the center of mass at any one moment, we'll use this definition that we wrote down. So with our 3 objects, that acceleration is this weighted average of the accelerations of A, B, and C. Those accelerations are weighted by the masses of A, B, and C. Let's look at one of these terms in the numerator. Mass of A times the acceleration of A. That looks familiar because from Newton's second law, the mass of an object times its acceleration equals the net force on that object. So this actually represents the net force on A, this is the net force on B, and this is the net force on C. So our numerator looks like the sum of the forces on A, B, and C, which is exactly what we wrote up above as the net force on the whole system, which we showed is equal to the net external force because those internal force pairs will cancel out. So in other words, this numerator here is just equal to the net external force on our system, and we've showed that the acceleration of the center of mass of a system will be caused by the net external force on the system and resisted by the total mass of the system. Okay, so that's our derivation of our new version of Newton's second law for a system of objects. And in the next video, we'll consider the implications of this law and look at some illustrative example scenarios.